Okay, if you ever wanted to go from polar coordinates to Cartesian coordinates, this lesson is just basically an intuition to kind of get you started where you don't need to memorize anything. You really only need to use your two basic concepts, one being your Pythagorean theorem, which is your x squared plus y squared equals r squared in our case. And then also you just need your SOHCAHTOA principles for trigonometry, your sine, cosine, and tangent. So given these two concepts, Pythagorean theorem and your SOHCAHTOA, you can solve any polar Cartesian problem that comes your way. So now this equation is very easy to solve for r. If we were given x and y, all we would have to do is take the square root of both sides of this equation. So that would leave us with r equals the square root of x squared plus y squared. So you see, if we were given the x and y coordinates, we can easily find what r would equal. Now let's go over to our SOHCAHTOA concept, our trig identities, and let's see how we can solve for theta if, say, we were given y and x again. Well, what do we know about our trig functions that has only the y and the x in that trig identity? Well, let's look at SOHCAHTOA. Our y and our x, well, our y is our opposite of theta, and our x is our adjacent to theta. So the trig identity that involves the opposite and the adjacent is our tangent. So we can write that trig identity, which is the tangent of theta, equals opposite, which is our y, over our adjacent, which is our x. And so now we have to solve for theta itself. So we take the inverse tangent of both sides of the equation. And so I'm just going to write it as arc tan of the tangent of theta equals the arc tan of y over x. And so that leaves us then with the arc tangent of the tangent of theta. Well, that's just theta. So, and so theta then equals the arc tangent of y over x. And if you think about it, this is just something that we learned a long time ago. To find out what theta was, we just take the arctan, we go into our graphing calculator and we take the arctangent of this number, and that gives us what theta is. So I was just doing it in an algebraic way so that we can see everything can be done algebraically by doing the same thing to both sides of the equation, which is what we did. We took the arctangent of both sides of the equation. So there you have it. If we were given y and x, our Cartesian coordinates, we could solve for theta. And in the same token, if we were given y and x, I should say x and y, we can find out what r is. So what if they wanted us to go the other way and say they gave us the theta and the r, and they wanted us to solve for x and y. Well, let's see what we would have to do to solve for x first. Let's look at our SOHCAHTOA concept again. What trig identity involves x and r and theta, of course? Well, x is our adjacent to theta, and r is our hypotenuse. So what trig identity involves adjacent and hypotenuse? Well, that's our cosine. There's our adjacent and there's our hypotenuse. So we would go ahead and write the cosine of theta equals, our adjacent is our x, and our hypotenuse would be then our y. So now solving for x, we just multiply both sides of this equation by r, and that gives us x equals r cosine of theta. So now we have an equation for x if we were given theta and r. Okay, well, let's try that again. Only this time, let's try and solve for y if we were given theta and r. So looking at our trig identities again, let's try and figure out which identity involves y and theta and r. Well, y is opposite of theta, and r is the hypotenuse. So we need a trig identity that involves the opposite and the hypotenuse. Well, there we have it, our sine. There's our opposite and there's our hypotenuse. So let's go ahead and write it. Sine of theta equals our opposite, which is our y, over our hypotenuse, which is our r. And then solving for y, we multiply both sides of the equation by r, and we get y equals r sine of theta. So there you have another quick formula. If you were given theta and r, you can also solve for y. So you can see that from our two simple concepts that we learned a long time ago, the Pythagorean theorem and our SOHCAHTOA, we have derived 4 formulas to go from polar to Cartesian and back again. Now the ones in red are if you are given your polar coordinates, theta and r, you could solve for x, theta and r, you could solve for y, and the formulas in blue are if you are given your Cartesian coordinates, x and y. So if you're given x and y, you can solve for r from the Pythagorean theorem, and if you are given x and y, you can solve for theta just from your tangent trig identity. So there you have it. And in our next video, we will go ahead and try some problems and just use all of these formulas that we have simply derived. And incidentally, forgot to write down our polar coordinates, how they would be written, and that would be your r, comma, theta. So there you have it. So this point here can be expressed in two different ways, as x comma y or as r comma theta. And if you think about your polar coordinates as, say you were standing right here at the origin, and somebody said, well, go ahead and direct yourself in a theta degree, say it's 45 degrees, so you would go ahead and orient yourself in a 45-degree direction, and then you would proceed to walk r units, whatever r is, if it's meters or feet or what have you, or drive r miles, or so on. And incidentally, as I'm looking at my little lesson here, if I really wanted to be color coordinated, I probably would want to say, okay, well, the ones in blue go from Cartesian, say you're given a Cartesian point of x and y, you can derive the polar from that. So it goes from Cartesian here to polar, and same with this blue. If you're given the Cartesian point of x and y, you can get to this other polar coordinate of theta. And in the same token, my red, we start with polar, so you're given these polar coordinates r and theta, and you can derive x from that. So, so let's see, so really should look more like this, where if you're starting with polar and then you're going to Cartesian, and then in the same breath the yellow would be red. So if we start it again, then our x and our y should really be in red, and then we'll just put our y there and our x there in red. Let's try that again. Okay. And then our thetas should, and our r should actually be in blue. So there's our theta, and there's our r. So now it seems like it all fits together. One other thing I would change, I would make my outline or my axes in white. So that they are a different color. Now it looks like everything goes together. And it may seem a little strange that, I went ahead and changed the colors and just kind of looking back at the lesson and so on, but that's this is something that we all should really do when we learn a new concept in math. We should always look back at the big picture and try to analyze what it is we did and how it fits together. And incidentally, I would like to look at it a little bit further, even what we have derived here. For instance, if we look at this part here in blue, we can see that it looks a little familiar to us. And if you recall, this is nothing more than the distance formula that we learned a long time ago. And it's the distance from 0, 0 here, from this point to this point up here, xy. So that's kind of where this comes from. The other thing we can kind of look at is what we have in red here when we're going from polar to Cartesian. Isn't it interesting that our x-coordinate is found by taking the cosine of theta? Well, yeah, the cosine always has to do with the x. So that should be something that we could actually just kind of keep in the back of our minds. And at the same token, our y coordinate is found by taking the sine of theta times r, of course. And, isn't sine something that we always associate with y? Well, yes, it is. So this all kind of fits together, and just kind of look it over a little bit and maybe re-watch the video and start to think about this in terms of think about it conversationally and how we can analyze it and so on.